In this problem, we're going to be investigating an application of differentials. Now, the application of differentials has to do with errors in measurements taken. So let's suppose that you measure the dimensions of a rectangular box to be 20 centimeters, 30 centimeters, and 40 centimeters with a potential error of 0.2 centimeters on each of those measurements. Determine the maximum possible error in the calculation of the box's volume, as well as the surface area. So we're going to split this up into two problems, and we're going to deal with the volume first. First thing we'll need to do is define the volume as a function of the three measurements associated with a rectangular box. That would be the length, the width, and the height. The volume of a box is simply going to be the product of those three quantities. Now, the total differential of this volume is going to represent the maximum possible error. So dV is going to be equal to, since we have a function of three variables, we'll be looking for a total of three differentials, or three partial derivatives, I suppose. So total differential is going to look like this. Partial of v with respect to L times dL, plus partial of v with respect to W times dW, plus the partial of v with respect to H times dH. Each of those differentials is going to represent the error in each of those calculations. Now, as far as some partial derivatives are concerned, the partial derivative of volume with respect to L, this will be L times a constant, so we will get the constant. For the partial of v with respect to W, this will be two constants times W, so we'll get just the two constants out of that. And the partial of v with respect to H, once again a constant times H, that'll be whatever the constant is, times dH. Now, it wasn't specified which one is the length, which one's the width, and which one's the height, so arbitrarily we'll say length, width, height, even though that wouldn't be entirely stable, having the height be the largest dimension. So with that in mind, W is 30 centimeters, height is 40 centimeters, and the maximum possible error in the length is going to be that 0.2 centimeters that we referenced just a moment ago. The length is 20, the height is 40, and the maximum possible error will be 0.2. Then length 20, width 30, and maximum possible error in height 0.2. Now at this point, if you're thinking of turning to the calculator, honestly probably a good idea. But I'm, me, so I gotta do it this way. That's 240 plus that's 800, 160 plus 600.2, 120. So that'd be, let's see, that's 400, 520. And the dimensions on this would be cubic centimeters, since we just multiplied a centimeter times a centimeter times a centimeter. Now, to let you know what this actually represents, this is only an approximation of the total error that we would have in our calculation of the volume, and I'd like to demonstrate how. Now, assuming that all of our measurements were correct, the volume would be 20 times 30 times 40, which we can see is 24,000. Now, assuming that we did have the maximum possible error on each of these, this would be like 20.2 times 30.2 times 40.2. You'll notice that the volume has increased, and the amount that it has increased by is approximately 520 cubic centimeters. Now, this, I guess, technically would be the largest possible error, that 523.608. But all that we've been doing within this section is approximating. So this would be the maximum approximate error in the calculation of our volume. Now, similarly, if I went in the other direction with this and subtracted 0.2 from each of these, we'd have 19.8 times 29.8 times 39.8. And if I subtract that number from our original volume of 24,000, once again, we get a number that is remarkably close to 520. So I guess the nice thing about the error is that it could potentially go either way. Now, if we wanted to do this same sort of calculation for the surface area, we would have to define a surface area formula. So for a box, there are going to be two sides of dimensions L by W, that would be the base of the box and the top of the box. We would have two front and back sides, that'd be a length times a height, and then two lateral sides on the sides of the box. That would be 2 times the width times the height. Now once again, if we're going to create a total differential for this, we would need ds. This will be partial derivative of s with respect to L times dl plus partial derivative of s with respect to w times dw plus the partial derivative of s with respect to h times dh. Now let's go ahead and plug in those partial derivatives. So differentiating with respect to L, we'll get these first two terms that both have an L in them. So 2w plus 2h times dl plus partial derivative with respect to w, we'll get two terms from the first and the third term, and the second term will no longer be present as it was constant. And for a partial derivative with respect to h, we'll get the last two terms remaining, and the first term was constant, and so it is gone. Plugging in the quantities that we know, this will be 2 times our width, which is 30, plus 2 times our height, which was 40, times our maximum possible error, 0.2, plus 2 times the length, that's 2 times 20, plus 2 times the height, that'll be 2 times 40, times the error, 0.2, plus, oh yeah, we're going to make this fit, 2 times the length, which is 20, plus 2 times the width, which is 30, times the error in that calculation, that is 0.2. Let's make this work. 60 plus 80 is 140. 1/5 of 140 is going to be 28. Plus 40 plus 80 is 120. 1/5 of that would be 24. And that's 40 plus 60, that's 100. 1/5 of that is 20. Adding all of these up, that's 20, 40, 60, plus 12, that's 72. Now this one, we took a one-dimensional quantity times a one-dimensional quantity, so that would be centimeters squared. And again, this represents an approximation of the maximum possible error in our calculation. Rather than demonstrating that with a calculator, I will say do something similar to what we did for the volume on your own, and that'll help explain what's going on here.